what I'm going to be doing today, if I can figure out what buttons I'm meant to be pressing, is working on this integration by parts technique. It's essentially, it's a process and a formula together. This is the formula. If you want to integrate two things multiplied, you do f of x capital G, take away the integral of f dash capital G. And it's pretty much a formula, but the reason it's a process is that you've always going to have this little integral and then you integrate it. And like L'Hopital, eventually this turns into something you know the answer to. But what we haven't focused on, that's what I'm going to start today, is that picking the f and the g isn't always as straightforward as you think. When you normally do, let's say from Calc 1, when you did the product rule, would you agree that it really didn't matter who f and g was because the formula worked, right? It was just f dash g, right? It does matter, integration by parts. So here are three main rules, and then there's a kind of, not really a rule, but a kind of fourth idea for different situations and how you choose your f of x and your g of x. First one is, if this expression here, if one of these is a polynomial, choose that one to be your f of x. So if you have to integrate something like x cubed plus x times sine x, or e to the 4x, or cosine of 3x, that kind of look, pick the polynomial as your f and the other guy's your g. I normally look at this as, who do you pick for f? Because if I know who that is, I can figure out the other guy. Well, that works for a lot of situations. Now, sometimes you're going to get a situation where there's only one function. And in this case, it's log x, but you might, in fact, you get a question where you're being asked to integrate the inverse sine of x, just one function. Whenever that happens, the rule's much easier. There's only one version. Make f of x the function that's there. So how come g of x is 1? Because you do need a g of x, right? You need to be able to integrate something. Why is it 1 in this situation here?
Because it doesn't change the answer, because there's only one. Fx is line x, and then if you add gx, line x times 1 is still line x. I mean,
yeah. Essentially, aren't you just calling that thing log x times 1? Right? And so the times 1 is the g, right? Now, in some situations, this rule 1 doesn't work. Now, I've put x here. I guess I should make it a little bit more obvious. I'll make it x cubed then. Right. According to rule or situation 1, should we be using f of x to be x cubed, right? It's a polynomial. But sometimes that doesn't work. And this is when situation or rule 3 kicks in. If one of the functions can't be integrated, you have to choose that one as your f of x. So I'm looking at this and I'll say, okay, one of them is x cubed, one of them is log x. I don't know how to integrate log x. Make that guy your f of x. Now, I haven't written this one down because I'm not even sure how I would say it, except, it's a big long sentence. If all else fails, if none of these three situations seems to exist in the question you've got, and there are so many combinations, there's bound to be a couple, then you have to rely on just a kind of general kind of feeling. Try and pick your f of x and your g of x so that this integral here becomes simpler. Now, you normally only have two choices. That guy's f, this guy's g, or that guy's f and this guy's g, right? So there's only two choices. That's at least something. So I guess there could be a kind of, in that same situation where you try and make it simpler, I could probably also add into that one. If you don't know or you can't figure it out, pick one. Just throw a coin in there and say, okay, your f, your g, let's see where it goes. And if it doesn't go anywhere nice, you've probably picked the wrong one, right? If this ends up being even worse looking than it was when you started, it's probably a bad idea, right? So what you would then do is just say, okay, switch places. If the first one don't work, the second one better. Are we good with this kind of hit list? Right. So today and tomorrow, we are going to be doing as much practice as we can. So let's see where I should start. Let's start a pretty straightforward one. This is question 3, or at least one of them. And this guy is going to be t e to the 4t dt. All right. Okay, I need an f of t. Right. I need a g of t. Who are you going to pick as f of t in this story? Who is f of t in this story?
T.
Yeah. Situation 1. Now, you want to differentiate this guy? You're going to get 1. You want to integrate this guy? Can we use that shortcut trick from yesterday? If you want to integrate e to the 4t, isn't it e to the 4t? What goes here? What goes to the left of it?
1/4.
Are we happy with that guy? Things good? Some windows that I need to move around, so sorry for my pause here. Right. Put the pieces together then, which is what we have here. And it's going to be f of t, capital G of t, take away the integral f dashed of t, capital G of t, dt. And this thing is t, and this thing is a quarter e to the 4t, take away the integral of 1 times 1/4 e to the 4t dt. Now make it look a little bit prettier. So that's what we get here. Now this one is pretty much finished because that integral we can get. One quarter e to the 4t. If you integrate it, you get 1/4 e to the 4t times another 1/4. So that's why that's now 1/16. And you're finished. Are we good with that? I've got a wee window. I've got a window issue. It's still not behaving. Okay, that'll do. Okay, any questions about that? It's, this is annoying. There we go. Why is this thing not doing what it's doing now? Darn it. Okay, pick another question. Let's see what we could do here. Oh, here's a version, question 5. Let's do w cubed log of w dw. Now, who are we going to use this time? Who's going to be f of w and who's going to be
W to the power of 3 and then log
Okay.
W.
So you're saying make that W cubed and make that log W.
Oh
So-
wait, but we can't do that. It has to be the other way around.
Right.
F of x is going to be log W, and g of W is going to be W cubed.
Right. And you caught yourself in time, and you kind of, I'm assuming what you did is you said, okay, when I use those combinations, what's going to happen next? And then you realize that integrating the log of W was a bad idea because it ain't going to happen, right? Now, do you see that that breaks rule 1, but it becomes rule 3? In fact, if you look very carefully, isn't that question?
Yeah,
same
that's
one.
what made me realize.
Right. So that's the subtlety in this. Do you see? You can't just say, make that the F, make that G, everything's fine. Right? You do have to look at your situation because it doesn't always work out the way you want it to do. Well, the W, the log of W has a derivative of 1 over W, and if you integrate it, it's a power rule. You get that. And so this integral becomes f of W, capital G of W, take away the integral of f dashed of W, G of W. What are we getting here? We're getting log of W times 1/4 W to the 4. Take away a derivative times 1/4 W to the 4. To make that look a little bit prettier, I'd probably put the powers at the front. If I want to make that prettier, shouldn't I cancel this W with one of those? And I would be left with that guy. But that's good news, isn't it? Because this guy can be integrated. He's just a basic power rule. So we have this piece. If you integrate that, you add 1 to the power and divide by the new power. Done. It's kind of elegant when it works, isn't it? You couldn't do that question with a U sub, right? It just wouldn't work. No matter what U sub you came up with, it just wouldn't work, unfortunately. Any questions so far? Okay. Get an idea when I do something. Let's have a look at the questions themselves. And we'll start here. We've done that one. Okay, we'll start here. And all I'm going to do is go through these questions, and we're going to talk about who you would pick for the F. Because if you pick the F, whatever's left is a G. So you only need to really figure out who you should pick for F. Right? Whatever's left will be G. In question 4, who will you pick for F of X?
Pi minus X.
Agreed, that would be situation 1. In question 5, we've just done, so I'll skip that one. Question 6, who would you pick for F of X?
One over x squared.
Correct. I know that looks like a fraction, but you have to think of it as 2 things multiplied. So it's 1 over x squared times log x. Who would you choose in 7?
X squared plus 7x.
Okay, that would be situation 1 again. Who would you choose in question 8?
Inverse cosine.
Yes,
To be a situation 2, right?
that's situation 2. Who would you choose in question 9 for F?
Situation 2.
Yep. Who would you choose for F in question 10?
log t.
That would come under the category situation 3. Who would you choose in 11? Who would f of x be in question 11? It's got you thinking, isn't it?
It's situation 2, right?
Correct. So it's the whole thing. It's f of x equals log x in brackets squared. The whole thing. Situation 2. What about question 12? Who is f of x?
X.
Yes. 6 to the power of x is ugly, but it can be integrated. It works. What about 13? Don't worry about the integral from 1 to 5 part. Just who would f of x be in 13?
Log.
Yeah. What about 14? Who would f of t be in 14?
Wouldn't it be t squared?
Correct. It's situation 1. Who would f of x be in 15? And I refuse to say that thing. Who would f of x be in 15?
Would it be situation 2?
Yeah. It would be inverse tan of 1 over x. Okay. The last few are kind of special cases because you have to make a u sub before you do it. We can ask you that at least. In question 16, what would be the u sub you'd start that question with?
Theta squared.
Correct, theta squared, and then it turns into a question, something, I'm not sure what the multiple is, it's hard to do in my head, but it turns into something like 5 halves u sine u, and then you do integration by parts. And this one here, well, no, we'll wait about them because they're going to happen tomorrow. So, right, so are we getting a little bit more comfortable with how you would choose your f and your g in these questions? So let's just return to doing some more examples. The more you see, I hope at least, that more comfortable the question's going to be to do. So let's do a really difficult one. This is question 8, or at least a version of it. Let me tell you right now, this one's weird in lots of ways. So we're really entering some sneaky questions here. Would you agree this belongs in situation 2? It's a single function on its own. So if you want to, you can think of it as 1 times that. But when you have a single function on its own, that guy is going to be f of x. And g of x is going to just be 1. That's how you take care of it. Now the derivative and the integral come next. Now that's going to get some cobwebs going. What is the derivative of the inverse cosine function?
Is it 1 divided by the square root of x squared minus 1 or x minus 1?
1 minus x squared, but you're in the right ballpark. And there's something missing. 99% right now, but something missing. Derivative of inverse cosine is 1 over the square root of 1 minus x squared, but what else is missing?
Is it plus minus?
Not plus minus, but just the minus. What is the derivative of the inverse sine function?
One over the square root of one.
Right,
Minus
that's,
x.
they're almost identical, aren't they? Just the negative because it's cosine. Right, now let's put this package together. So it's going to be f of x, capital G of x, take away the integral of f dashed x, capital G of x, dx. I kind of warned you at the beginning, this one is going to go some weird places. Well, that guy is just the inverse cosine of x times an x. Not too weird about that. The derivative is really ugly. Times that. And then I'm going to make it look a little bit prettier. Two negatives make a plus. And you probably were not expecting that to happen. That's why this is a weird one. This is the integral that we need to find, because once we know that, we've got the answer. I'll put it over here. What technique will you use to solve that integral? And it's not integration by parts.
Use of.
Nailed it. Who's the use of going to be?
1 minus x squared.
I like this question because what can happen in a lot of situations is you just do the same process 12, 15, 20 times and it becomes kind of mechanical. Do you notice that you have to always be aware that maybe you have to do more than one technique to get the answer? Okay, this started life as an integration by parts, but didn't this piece of the puzzle have to use a different technique? So it's not that unusual that you have to bring in other techniques to, to finish the question off. So let's do integration by parts. If you differentiate it, you get that. You do the crossover, you get that. You divide, put the minus up there. You divide by 2x, and you get that. So we have the integral of x over the square root of u times -1 over 2x du. Cancel out the x's and I'll bring that -1/2. I like to separate them. And we've got that. Oh, that's a bit annoying. I was hoping to get something nice there. I can integrate that. What do I need to do?
It's funny power rules.
Yeah,
-1/2.
-1/2. You remember doing that way back in week 1, probably. Right, now I can use the power rule. I will add 1 to the power, and I will divide by the new power. Well, dividing by 1/2 is the same as multiplying by 2, so guess what? You get that. Which then becomes that, which then becomes that. So with a plus c, I guess. So this integral is this fella. So we now have x inverse cosine of x minus that guy plus c. Can you imagine being the head of, early mathematicians at Newton's time? Okay, they probably called them arc cosines in those days, but I would use it in that context, historical. And you're trying to find the integral, the antiderivative of that. It's a very simple function, right? It's just a one-off function, inverse sine, inverse cosine. What possibly could go wrong. When you look at its antiderivative, right, its integral, would you agree that you would probably never guess in 1,000 years that the answer to this was that, if you were only going to do it by, oh, I'll guess what it should be. Now, if I was going to guess that, do you know, I'd probably think it might be the inverse cosine. The inverse sine. Would that seem a reasonable starting point? Oh, the answer's probably got inverse sine in it, right? Cosines get you sines, so inverse cosines probably get you inverse sines. Not a sign of an inverse sine anywhere, right? Without this technique of integration by parts, that would have just remained a mystery, I think. Nobody would have probably came up with it unless they were really lucky. So, I'm moving up maybe too quickly. Are we good with this question? Can we move on? Okay. I haven't done them yet. Let's do this guy. Now, we know the answer is not 1 over x, right? That's what the derivative of that is. Who is f of x and g of x in this story? Who is f of x and who is g of x in this question?
F of x is ln x and g of x is 1.
Right. Do you agree it's another situation 2 story, right? So the derivative of this guy is 1 over x, and the integral of this guy is x. So I guess I should call it ln of x, right? So this fella is f of x, capital G of x, take away this guy, dx. So we've got a natural log of x times an x. Take away a derivative times an x. So I like put the x's at the front, and that becomes the integral of 1 . Wow, wasn't that a nice clean one? Nothing too strange happened. We cool with that one? Any questions? There is one that's like it, but it has a little extra piece in it. So let's see if we can figure out a way to do that one. I could tackle this question in the same way that I did this one. In other words, make f of x the natural log of the square of x. But I'm actually not going to do it that way. Isn't a square root a half power? And can't those be brought out to look like that? Now, if I rewrite this integral as this equivalent, can't I then do f of x is natural log of x and g of x equals a half? Would you agree I could do that? That would count as a situation 3. Right? You can't integrate this piece, so make it f. Now, why do you think I decided to go this route instead of making that whole thing f of x and g of x1? Because the alternate would have been, and it would have worked. Right, this would have worked. I'm not saying it wouldn't. But why do you think I went this road instead of the more obvious road? Any ideas why I went that way?
Much easier in the resulting expression.
I'm not sure. Say it again, James.
Is
Didn't
it
catch
much easier to deal with the f of x and g of x that you get?
Would you agree that this guy's just 1 over x? Would you agree that's a pretty easy thing to differentiate? If you're going to differentiate this guy, don't you have to be really careful because it's a general? It's not just the log of x, isn't it? The log of the square root of x. So won't the answer be 1 over the square root of x followed by the derivative of the square root of x? And trust me, my experience has been if you try and do something that's it's easier to do something that's simple than it is to do something that's messy. And so I tend to make fewer mistakes when I do it that way. But ... you could finish that. Where shall we go next? Let's try a version of 11. Now, we already spoke about who we should do here. This is situation 3. So in situation 3, if you can't integrate anything, in this case there's one function, you can't integrate it, I could call it that. I guess it also qualifies as situation 2, doesn't it? So it's a bit of A and a bit of B. Now, the derivative of this guy is not going to be pretty. The integral of this guy is. Would you agree this is a chain rule? It's a something squared. So the derivative is not just 2 log x's. That's what people forget when it's a chain rule and they don't realize it's a chain rule. It's 2 times log x to the power of 1, which is 2 log x. But what else is missing? You finish with a times something. And isn't it the times the derivative of that guy? You see? Now, are you okay with that? That's the derivative of log x squared. You okay with that? So we can now move into our guy, and it's going to be f of x, capital J of x, wrong shape, minus f dashed of x, capital J of x, dx. So it's going to be the natural log of x squared times x, take away 2 natural log of x times 1 over x times an x. And we now have that guy squared, take away 2 times the natural log of x's, because the x's cancel out. Okay. Would you agree that I will have to do integration by parts one more time? Right, to get this piece, I'm going to have to do integration by parts. Here are my 2 pieces. Which one of those 2 in the 2 log x is going to be my f of x?
Log x.
And off you go, and dot. So we haven't had too many questions today where you had to do integration by parts twice. So here's the first one for today that you needed to do that. Are we good? Any questions? Okay, let's do a version of 12. The integral of x 6 to the x dx. In this question, the choice of f of x and g of x are actually pretty straightforward. And the derivative of this one is very nice. Okay, time to brush out the cobwebs. What is the integral of 6 to the x? I'll tell you the bit that's easy. It's got a 6 to the x in it. But what's missing?
Divided by ln6.
Nailed it. How come you remembered that one? Is it just weird and it's stuck in your head?
I remember doing this one in the homework.
Oh, okay. Did you have to go and look it up the first time?
Maybe.
That's okay. The more you see something, the better you get. So we're good. So we've got x, 6 to the x dx. And it's going to be f of x, capital G, take away the integral of f dashed x, capital G, dx. And this is going to be x, and this is going to be that ugly mess. Take away 1 times that ugly mess. Okay. I'm not quite sure how to write this. It's kind of ugly no matter how I write it. So I'll try my best. That guy. And that guy. Okay, we're going to integrate this guy. You know that ugly log 6 in the bottom, isn't it just a number like 4? It doesn't really do too much. So we're going to have this guy. Integrate that guy, you get 6x divided by the natural log of 6. You've already got 1 there, so if you divide it again, you're going to get a square version of that, and technically a plus 6. So far, so good. The integral of this is that. You comfortable when you integrate this guy, you get an extra log 6 in the bottom, now you've got a square. Well, let's add something to the question. Let's suppose it's integral from 0 to 1, which it is actually in the one I'm looking at. That plus c disappears. And what you get is the limits of integration from 0 to 1. So what I tend to do in these questions is I pretty much don't even worry about these limits of integration. They kind of confuse the issue and they just muddy it. Just do the question the way you usually. But when you get to the end and you would normally do a plus c, stop there and then just put a bracket around it and do the start and finish. And to me, that just makes life easier. Otherwise, you have to put it in various places, and there is a chance that you'll kind of maybe do it too early or too late. Right, if we plug in 1, it's going to be 1, 6 to the 1, log of 6. Take away 6 to the 1, natural log of 6 squared. Minus, well, if you plug in 0 here, you're just going to get 0. And if you plug in 0 here, you're just going to get 6 to the 0, which is 1. So you're going to get that guy. And so what I've got is 6 over log 6. Take away 6 over log 6 squared. Take away nothing. Take away that guy is add. And these are the same. So it's a very ugly answer. I think, Eric, it was you. You've already done this. Was WebAssign happy with that, or did they want a style point?
I'm gonna be honest, I just input the line after that one. I mean, for that one. So like
Okay.
the 6 ln6 minus 6 ln6 squared plus, yeah, that one.
So it was it happy at this point?
Yeah, it took that answer.
I wish it hadn't, because I mean, now that you see it, it kind of makes sense that you could do a little bit. I'm not sure which else I could do. I would be happy in an answer in a test like that. But anybody want to have a shot at making that look prettier?
It's
I've
by
got an idea.
6 over log 6 by log 6 on both sides. So you
So-
get 6 log 6 over log 6 squared. And then you subtract and you're left with, 6 log 6 minus 5 over log 6 squared.
Right. Yeah, and that's exactly what I would have done. And now that I'm seeing it, I'm thinking it was pretty ugly before. Would you agree it's just as ugly afterwards? So I'm not really thinking that I did much to improve the answer. So, that's fine. Anyway, if you're doing an exam and you're kind of worried about what's the best version of the answer, I would not like this one. I mean, you'd get 19 out of 20 points. I wouldn't take a lot off. I would like this one. And if you keep going and making it into other things, what I tend to do is I stop looking at the line I was voting to see. And then if you travel on and do some other stuff, then that's fine. I won't take points off. Even if you do other stuff and it's wrong, I still won't take points off because I'll think, hey, you got the right answer and it's in a form I'm happy with. I would stop there. So when you're doing style point issues, if you've got the time, see if you can make it look prettier. Yeah. And don't worry if it doesn't quite work out. Are we good? Any questions? Try to think of one more. Oh, okay, this is one. Last one for today. It's going to be t squared sine of 2t dt, and it's going to be from 0 to 3 pi. Just ignore the 0, 3 pi to the end. That's my advice to you. Okay, so we need to pick an f of t and we need to pick a g of t. Which one would we pick for f of t?
Sine of
squared.
2t.
T squared.
Sorry.
No? Don't know why you should, sorry. You're interrupting. Yeah. You can't help that. If you notice in Zoom, we don't get the same physical clues that you get in a room, so you don't know someone's trying to speak when you're trying to speak. It's awkward. You can't avoid it. Differentiate this guy is 2t. Okay. Can we do the shortcut on this guy? Right. What is the integral of sine 2t? Should be able to do it right away.
Negative cosine.
I hear a 1/2.
Oh,
Okay.
my bad.
Keep
Sorry.
going. No, keep going, somebody.
Negative cosine.
Yeah.
Okay. Agreed, everybody? Cosine and a half, put them together, call it good. Okay, so the integral of t squared, the sine of 2t dt is f of t, capital G, f dashed of t, capital G, dt. And we have t squared times this guy. Take away 2t times this guy. Make this a little bit prettier. It's -1/2 t squared cosine of 2t. That's negative, so is that. So it's a plus, that's 2, that's a half, they cancel out. So I'm left with this fella. Would you agree we just have to do integration by parts a second time? And f of t will be t and cosine 2t will be the g. So it's going to need some more room, so it's going to be over here. Writing down the integration by parts formula. To remind you, he's my F, and this piece is my G. So we have this fella. And let's go. It's f of t, which is t. If you integrate a cosine, you get a positive 1/2 sine of 2t. Take away 1 times positive 1/2 sine of 2t dt. So we now have negative 1/2 t squared cosine of 2t plus 1/2 t sine of 2t. Almost done. And then this fella. And if you integrate a 1/2 sine 2t, you get negative 1/4 cosine 2t, and negative 1/4 with this negative gets us plus 1/4 cosine 2t. This guy is still the same. And finally, this guy is still the same. Now, if this question did not have limits of integration at 0 and 3 pi, I'd put a plus c here. But since it does have those limits, it's at this point here that I introduce them. We're comfortable with that? And we're running short of time, so can I just say ... Wouldn't that just be a matter of plug and jug? You'll get 1s and -1s and 0s all over the place. And last name. And that's us for today. I'll hang about for any questions.
Professor,
Yes.
I have a quick question about homework 6.4 again. Let me show you the screen.
Okay, there you go. You've got permission. You should be able to share.
Yeah. This one. Could you see it?
Yeah.
Number 13 though, but still I was
right
not sure about the parentheses after the integral, like after the limit.
Yes. Right. The fact that you got the right answer, you know, the third one, 4829.
Right, yeah.
What that is telling me is that you're doing it correctly. So you might be saying, well, why am I not getting the integrals right? There are two ways to measure x. You can measure x from the top going downwards, or you can measure x going upwards. And here they're saying, let x be the height of the meters above the ground. So that means you're going to have x going that way instead of x coming down the way. The net effect of that is that this formula will get changed.
Right.
And whatever this formula is, this will become the same guy. But although the formula gets changed, you're still calculating the same thing. So of course the answer will remain the same. So if I can just take some of the notes, the numbers here, I'll show you how that would be set up. It's a 10 kilogram bucket. The height is 14 meters. The weight of the rope is 0.6 kilograms per meter. And the water starts with 42 kilograms, right? I think I've got all the, oh, and we've got gravity of 9.8. So gravity has to be added into this story as well. Okay, and I'll take back permission now and I'll give you the setup. So here's my little guy. This distance is 14 meters. And We're going to choose a random position here, but we are not going to count X this way. We're going to count X that way. Oh, you can't see any of this.
Yeah, I cannot see.
Okay, so come on, there we go. So here's going to be a 14-meter cliff.
Right.
We would normally, I like to count it from the top because the formula says here, but they sometimes count it from the bottom and it's allowed. And this is going to be the X variable, right?
Uh-huh.
What else do I know? I know that, well, let's see what I know. I know the rope is that, that's good. If you take the 42 and divide it by 14, right?
Right. I
What
guess
you get is the rate of water thing. So I guess I'll need that. So 4.2 divided by 14 comes out as 0.3. So that's how much we lose per meter in
Oh,
water.
is it 0.3?
I'll check it again.
Oh, I think it's 3.
It's 3.
Yeah.
Yeah. I put a decimal in for some reason. So it's 3, which is a nicer number. Okay, let's find that force function. Well, it's made up of the weight of the rope, the weight of the bucket, and the weight of the water that's left. And because it's metric, there's going to be a 9.8 tagged on at the beginning. So it's going to be 9.8 times these things. So
Right.
what do I know about the weight of the rope at this point here? And then what the weight of the water is? Well, I don't like this direction because it's messy to calculate, but we can do it. If from here to here is X,
Right.
then won't this distance be 14 minus X? That's 14, this is X. Won't this piece here, the rope that's left, be 14 minus X? You comfortable with that?
Yes.
And the rope weighs 0.6 kilograms a meter. So 0.6 times 14 take away X. That's the rope. That's that bit done. The bucket is just 10. So far, so good?
Yes. Yeah.
Now, if you raise this thing up X meters, and for every meter that you raise it, it loses 3 kilograms, then the amount of water that's left here is what you started with, which is 42, take away 3 times X. Right. You've raised it X meters, you lose 3 kilograms every one of those X meters. So you're losing 3X. So the water that's left is 42, take away what you've lost. Now, if you take this expression and you multiply this guy out and you add all the X's and do all that stuff, let's see what we've got. 0.6 times 14 is 8.4. Take away 0.6X, add a 10, add a 42, and take away a 3X, right? So you take all of those guys and you combine like terms. On the numbers you get 52, what's that? 52, 60.4. And when you do this and this, you get take away 3.6X. And that's the guy that they're looking for.
Oh, I see. So is that basically what I need to plug in the both parentheses, like after the limit and after the for the force function?
Yeah, let me double check on that, but that's my, oh, darn it in space. Can you share your guy? No, don't need to share. I'm going to figure this out in a second. Okay, it's work done. So let's do scores. I'm going to show you yours, which that's probably the easiest way to do that.
Right.
Right, so here is that. Are you seeing the screen yet? No.
Oh, I'm not seeing
No,
the screen,
Okay,
but I'm
is
thinking
this
about
is question 13 or
13.
15? It's 13, I think, isn't it?
13, yes, 13.
Let's get that out of the way. I'm almost there. Okay, now I can show you what they did. That's not what I want to do. Turn it space. Just hold on, I'll be there. Here we go. Are you looking at your question 13? Do you see my 9.8, 60.4 take away 3.6 xi?
We're looking
no,
at 14 on your screen.
You
Yeah,
are
yeah, on
looking
the
at the wrong one. Okay, let me figure out where that screen is in all my screens. I think it's here then. Are you looking at it now? 13.
Yep, I'm seeing
Right. Do you see my 9.8, 60.4 take away 3.6 xi?
that. Uh-huh.
That's what they were looking for. So they just counted it from the bottom up instead of from the top down. I still like my way of doing it. I think it's less work.
It's
Right.
also much cleaner.
It's a lot cleaner. You're right.
Yeah, I see that, but yeah.
But the interesting fact is that it's, if you integrate that, it's the right answer. It's 4829. So it's not that oh well, if you go it this way you get one number, and if you do it the other orientation it's a different number. That would be scary, right? All you're
Yeah.
doing is looking at the same puzzle from two perspectives.
I understand.
Cool.
Thank you.
Normally as well, it'll allow for different like ways of reaching the answer, but
You would
because the
hope.
X is
Yeah.
yeah, because it just like plugs in random numbers for X and makes sure that like it comes out to the right math in the end. But since these are approaching it from two different ends, the math doesn't align. So it could say
Correct. The math doesn't align, but the answers do, thankfully.